get started. As a reminder on some course logistics, homework 5, the last homework, that's due today, right, Sid? November 14th. And that is the last homework. So after that, all you have to work on is your class projects. Today we have a guest lecture. We have Kwok Lei and Barrett Zoff from Google. Kwok did his PhD at Stanford University with Professor Andrew Ng, and at the time he did a lot of this kind of earlier deep learning work on large-scale unsupervised learning, which may be making a comeback at some point in the future. Certainly in the world of NLP, it seems to be a big deal now, but back then it was in the world of computer vision. Kwok then was involved in some of the pioneering research on neural machine translation. I would guess actually if people have like an Android device and there's some kind of like machine translation going on, probably the technology that you developed is in there somewhere. And these days he works on large-scale kind of neural network architecture search and automated machine learning together with Barrett Zoff. So please.
Yeah. Can you hear me? Okay. Hi everyone. My name is Kwok. I also have with me today my colleague Barrett Zoff, who worked with me on a lot of projects in automated machine learning. So this is John worked with many other people at Brain as well. So not just the two of us. Just before we begin going to all the details about the methods and like the detail of the results, I want to tell you that like we have made significant progress in using automated machine learning in the area of computer vision. So we started our projects around 2017, and before 2017, this is the Fa18 dataset. You're probably familiar with the Fa18 dataset. Before we work on automated machine learning, most of the state-of-the-art in this area are human design networks. So you can see here the famous ResNet model and wide ResNet and DenseNet, which is the best paper award in CVPR last year, I think. And then Shake is a regularization technique for ResNet. And now, since we started working on automated machine learning, the top 3 best models on Fa18 are automated, are designed by computers. On ImageNet, the same story. So you see here, before 2017, most of the state-of-the-art on ImageNet are human-designed models. So you see here the famous VGG network, Inception, ResNet, and Pyramid network, Polypath network, and so on. And now, with reinforcement learning and some evolution, we also, the top 3 best models in ImageNet are designed also by like automatically. Okay, so let me get a step back and tell you the motivation of our project. So, so I have been at Google for since I was an intern in 2011, and I work on many projects in machine learning. And every time I work on every project, my impression is that once you have data and you have computation, you're done. You just give data and computation. You get the job done, you get a model launch. Unfortunately, behind it will take months and months of effort of tuning the hyperparameters, tuning the learning rate schedules, tuning the architectures of the model, the weight decay, etc. So many hyperparameters. And in reality, we need months of work in order to get a good model. This is the story that I've seen in, so I work on a computer vision model for Google to do street view recognition. Also, I also work on speech recognition for Google, and it's the same story, and also translation. The reality is that we need machine learning expertise, and machine learning expertise becomes more and more rare. It's harder to get people to have insights and knowledge to design inceptions network or to design better translation network. And every time you go to NIPS, you get a new paper, and there's a new architecture component proposed by somebody, right? So it's just a very, very good intuition somewhere. So the question from us is, can we turn this into more like a computation-driven approach? Can we say that we have data and then lots more computation, right? Maybe it's harder to do it maybe 5 years ago, but now we have a lot more computations. The TPUs are still not busy enough, so let's try to use 100 times more computation, and hopefully we're going to get some good things. A lot of our work has been focusing on vision, but like the ideas behind our method can generalize to other areas. But we started in vision with the following observation. So I'm personally following a lot of competitions, cargo and ImageNet challenges and so on. And I'm intrigued by this very interesting result that on the ImageNet challenge. So, on ImageNet started out around 2012. We have AlexNet, which achieved around 55% accuracy, top 1 accuracy. And over the year, you get up to like 80% top 1 accuracy. Now, interestingly, behind this, there's the validation set. This is the accuracy on the validation set, and the validation set is the same. So you get from 55 to 80%, which is 25% gain in accuracy just by doing better architecture and hyperparameter design. So the question is, can you automate this process? And turns out, like, for example, if you look into a famous Inception V4 computer vision model, you see, you know, it has a 1 billion block that look like this. You have a bunch of filter concatenation, and then you have a lot multiple branch. And you look into it and you ask yourself, like, why are these branches? And it actually is through trial and errors. So I talked to this person, Christian Zagady, and it's basically, you know, he sat down, he tried this approach, he tried that approach, and he see that, oh, these two approaches gotta get some improvement, so let's combine. So if you think about it, it's very much like try and error. It's like playing computer games. Yes?
One question. Do they change the training set every year?
No. So the training set is the same, and the validation set is also the same. Now if you participate in the contest, there's a test set. It's different. Now, this figure is a test set. It's usually people report it on the validation set, and there's a strong correlation between the validation set accuracy and the test set. And here I'm just plotting the validation. Yeah. Now, in reality, I think there's some fluctuation because every year they change the test set, but this is basically the figure you see. Everything clear? Oh, by the way, you feel free to interrupt me during the lecture. You can ask questions. You see this right away if you take a look at the famous Alex Krzyzewski's ImageNet 2012 paper. This is the architecture of what called the AlexNet, right? So it started out with an image of 224 by 224. And then you apply some 11 by 11 filter with some stride of 4. And then you do convolution in the image. And then you do max Boolean. And then with 48 filters here, right? And then You go to 128 filters, you do max pooling, you do 129 filters, 129, etc. And then at the end, you have fully connected networks, two fully connected layers, and then you have a softmax. You look at this network and you ask yourself, why is the image 224 by 224, and why we have 11 by 11 filters? And then why do you end up with max pooling here, not over there, right? Things like that. For example, in these two layers here, there's no max pooling. So you can just see right away that this process has to improve somehow. So we around 2016, Barrett and I started looking into how we can actually automate this process. And our intuition is the following. It's very much similar to what Christian Zagady was doing. He was basically playing a computer game. He was running in one experiment. He generates some program, right? And then he train it, and then he get some kind of signal coming back from him. And then he will look at it and say, is it improving or is not improving? And then he uses that signal to actually, over time, through a lot of insights, maybe a few hundred experiments, actually a few hundred experiments for real, that he actually come up with a good network. And we mimic that idea. So here's how we mimic it. We say the key idea is that if you have a convolutional network, and no matter how complicated it is, it's actually it's basically a little computer program. Right? And we know there's a good method to generate that computer program is you use a recurrent neural network. Right? It generates one token at a time, and then you generate the whole program, and then that program will be executed on your data set. Right? It will be trained and evaluated. Some programs are going to be not being able to compile, and some program can compile. And some program will give you 5% accuracy, and some program will give you 60% accuracy. So the controller, namely the RNN, should basically learn that 60% is better. So over time, it will basically generate more programs to look like the 60% rather than the 5%. Now, and then the training signal is basically the reinforcement learning signal. Back at the time, we used basically the basic reinforce, so it's kind of very expensive. But over time, we actually now we started using more like PPO kind of algorithm, so that it's the sample efficiency is better. But this is basically the picture that you should. This is the kind of a takeaway picture. So you have a controller. Now it's basically in the form of a recurrent network that is actually proposes models in like a little computer program. And that computer program is in like a domain-specific language, because it cannot be TensorFlow, right? Because TensorFlow is too complicated. So we create like a little computer program that looks more like a cafe configuration string, right? And then that cafe configuration string will be executed on your data set. So it will be trained and evaluated. So imagine like when you train ImageNet, right? Every iteration will take like less than a second. Every time you train, every iteration of this, you basically take a few hours, because the network, the child model there, needs to be trained and evaluated to get some accuracy. And the accuracy will be evaluated on the validation set, like a separate validation set, so that you measure generalization instead of overfitting. Anyway, you have a question?
How did you initialize the child model?
Initialize, you mean how initialize the weights of the network? Or?
How did the initial architecture of the child model was chosen?
Oh, at random. So basically the controller, at the beginning, the controller will sample like a random string, and it will be evaluated on the data set.
And
yeah.
Also, what's the action space for the controller model?
Yeah. So I will get to it in a sec. So okay. So the domain-specific language can be like this. So let's suppose that let's ignore all the complexity of a ConvNet and say every layer in the neuron in the ConvNet is just convolution. It's a convolution everywhere. So this is just to see how you can make it very easy. So let's suppose that it's convolution anywhere. So the decisions you're going to make would be how big are the filters and the stride that you apply for the filter, right? And the number of filters of that layer. So, okay. So the controller will do this. It will say, let's try to make a decision for a particular layer. Let's say this is layer N that you're trying to make decision. It will first generate the filter height, filter width, stride height, stride width, and the number of filters, right? And then it keeps on going. So at the end, you will have it will terminate at some point, right? So you will take that network and then construct your convolution on that. Now let's suppose that you want to insert in insert the layer type. You can too. You can just say have a node in the recorder network to predict the layer type. So it could be the softmax in this network. We choose between, you know, a pooling layer or a or a convolution layer or a local contrast normalization layer or a batch norm layer, for example. But like all the decisions will be similar too. Yes?
How do you choose the number of rollouts for this kind of architecture?
Okay, so ideally what we want is that like at the end the controller will just predict like an EOS somewhere, like n upstream, right? But like we experimented with it, it doesn't work very well. So what we did was basically we fixed the max length to be like 50 or something like that. Any question? Yep, you have a question.
Does the RNN also choose the activation functions, or is that just fixed for each layer?
It's fixed for now. I will get to that part in a second. So when the softmax classifier will generate a bunch of like actions, right? And then each of action will have a probability. So the probability of the entire program will be the multiplication of all the probability. And then you have a reward signal, which is basically the accuracy of the model. So you multiply it up and then take the you call TensorFlow to get your the gradient with respect to the parameter of the controller.
Question?
Yes.
How you change this how you get the gradient in this
Yes. So the RNN will generate a bunch of probabilities, right? The probability is a function of the parameter of this network, right? So the probability of the program that you're generating is is a product of all the probabilities, and then you scale by the reward, which is the accuracy of your model. And then when you take the derivative, you just take the derivative with respect to the p, which is the function of the network.
So you use reinforce too?
Yeah, just use reinforce. Initially we used reinforce, but now we switched to something like PPO. Yep.
Have you thought of like using continuous choices basically at each of these like bullet points, like filter with being continuous instead of discrete?
Yes, we haven't tried ourselves, but there's some other teams at Google who actually took this controller and they tried with continuous control, and it works too. Yeah. We were kind of lazy. We say, okay, just discretize everything and then just do the discretization method. But yeah. So again, basically, we train with reinforce. So we want to compute we want to maximize the expectation of the reward, right? And so they expect basically the actions. The actions are basically the architecture, the prediction of the controller RNN. The reward is the accuracy of the architecture on a separate held out data set. So let's suppose that your data set has like 50,000 examples. You create a separate like 5,000 example for accuracy, because that way you can measure generalization, not just fitting, right? And you can just expand it, like the way I said. The probability is the probability of a softmax given previous action and the parameter, and then you just use reinforce to compute the gradient. And then you basically, in our implementation, we have a distributed implementation where we have many child models, not one at a time. We have like 100 at a time. So this way we can use a lot of GPUs at Google. First, I'm going to show you some experiments that we did on CFA10 and Pantry Bank. I don't think we include the Pantry Bank experiment. So let's go to CFA10. So our goal is to evolve a convolutional neural network on CFA10. And the result is that we actually, at the time, we get state-of-the-art accuracy on CFA10. And so let me show you. So first, we predict the fixed number of layers. So the number of layer n, we say we choose whether it's 15 or 20 or 13 or something like that, right? We have to choose the fixed number of layers, determine ahead of time the fixed number of layers. And then we have to predict the filter width and height, the stripe width and height, and then the number of filters. So it's like this. So at layer n, we have to choose, the softmax have to choose between 1, 3, 5, 7, which is the filter height, and 1, 3, 5, 7, filter width. And then stripe height 1, 2, and 3, and stripe width 1, 2, and 3, and then number of filter between 24, 36, 48, and 64. And then, it turns out that in practice, a lot of new convolutional networks have skip connections too. So the search space that I just told you didn't have any skip connection. So we want to have skip connection. So we have some kind of anchor point around here. And then we do attention to the previous layers and say, sample me the layers that I should connect to. So it will generate a little, like maybe 5 other layers that I should connect my my current layer to. And then that anchor point is also like a softmax. And then you can just sample, and then you also get a probability. So and then you can generate. So in terms of experiment, we, as I said, CFA10 had 50,000 training example and 10,000 example for test. So we take 50,000 example and split it into 45,000 for training and 5,000 for validation. Now, and then each of the child model we train for 50 epochs. And this would be for how long, Barrett? Few hours of training.
Like a few hours, maybe like 3 to 4 hours.
3 to 4 hours of training. And the total number of child models we train is around 13,000 models.
Yeah, you know what? I think it was even maybe a little longer than 3 to 4 hours.
Yep,
I think the whole thing took about maybe like 3 weeks to run.
3 weeks in total. Yeah, 800 GPUs. So
A lot of resources.
lots of resources. This is I said this is the best way to use a lot of GPUs at Google to solve CFA10, which data set that nobody cares about. And it will design a network that look like that, right? I think it's the font is a little bit too small, so I can't. You might, it's hard to see, but you see that it's actually pick like a filter height and width very small down here, and bigger filter height and width up there, and it tries to predict like rectangular kind of filters, which we normally don't do. Like when I create a convnet for CFA, I usually like 3x3 or 5x5 or 7x7 size kind of filter. This network doesn't like it. It likes, sometimes it says 7x3 kind of filter and 7x1 filter. And it will also make a lot of skip connection in a very irregular pattern. So we did a control experiment where we said, oh, let's connect everything. And we didn't get, the result is worse than this network. So it actually finds a network that actually quite optimal in some sense. Yes?
Did you introduce any priors where you wanted to bias it towards filters that you would expect to be more human designed to see if those were significant?
Oh, we did not do that. That's a good idea, but we never done that. I think we did some control experiment where we basically say connect all the layers together, which is dense net kind of look like, and we didn't. The result was worse. And in fact, like you can see from this set of result, kind of we beat almost all the result of the dense net, except for one dense net that actually very, very, very deep right here. So in terms of results. So I think people have improved this result a little bit since then, but actually architecture search also improved. So we still very much state of the art. But back then, here's the result. So I think we at 3.65 error. Lower is better, and the state of the art back then was around 3.7 and 3.5 kind of percent. And by the way, this data set, many people have worked on it, and it's been around for like 10, 12 years. So there's a lot of papers. This is probably one of the most benchmark data set in machine learning, together with MNIST or something like that. Yep.
Are all of those previous architecture a subset of your search space that you've been like exploring?
Some, not everything.
But they were like, I mean, your architecture should be like more optimum in terms of layer, I guess. Like that depth is smaller than like some dense networks.
Yes.
Although you didn't cover those spaces, the things that you found are acting better than like those more complex.
Yes. So for example, some networks have this stochastic depth, right? We don't have stochastic depth. I think ResNet is kind of in our search space. So ResNet kind of works, but you see the best of ResNet is about 4.6%. So yeah, the best of ResNet in the original paper was like a 6.6% and things like that. So I think our search space covers ResNet, DenseNet, which are some of the networks that kind of work well on this data set. But we find better networks. Yep.
How much do you think this architecture is specific to this data set versus to images in general versus to natural images versus handwritten digits? Like how far do you think the story in general is?
I see. Hard to say, but we have in the next part of the lecture, I will tell you about an idea where we trying to learn architecture that transfer from one data set to the other. We haven't done any experiment where we take this network and apply on, say, MNIST or ImageNet or something like that. I think it might be a little bit optimized for this particular data set. That's my gut feeling, but we don't have data to back it up. Yeah, I think if you do grid search, I think the search space is 10 to the 15 or something like that.
Yeah, it's like it'd be like insane.
Yeah, you can't do that. You can't do grid search.
The search space is even much bigger than that too.
Yeah. In the paper, we mentioned the number, and I don't think it's possible to do grid search because if you can do grid search for hyperparameters, right? Because you might end up with a learning rate and maybe a weight decay or something like that. So the search space for hyperparameter is actually quite small, whereas an architecture is much larger. If you think about it, right? The number of layers and the possible choices that you can make in each of the layer is a lot higher. So I think it's unlikely you can do research. I think the number of models that we generate is absolutely for sure that it's less than 1%, right? It's a substantially very tiny area of the space. Yes.
So just based on the learning rate, you didn't tune the learning rate. You didn't search for the learning. Did you search for the learning rate in your model?
So usually in our method, we try to find an architecture first, and when we find an architecture, we have like a little grid search to find the hyperparameter like everybody does, right? We gotta search for.
When you search for the architecture, like
We
you use like a fixed.
Yeah. We use a fixed scheme, and one favorite scheme that we use is basically the cosine learning rate decay. Yeah.
So the other thing is, do you prefer simple networks in your search, or you don't care?
We don't care. We don't care. Yes. Like we had some idea about like enforcing some kind of regularity in the model design, but we didn't do that in this paper. Yeah.
How do you pick the hyperparameters of your top level like agent? Because you said it takes like 3 weeks to train, and then if you cannot really do hyperparameter tuning on top level, right?
Mm-hmm.
Oh, you mean for like the controllers, the
Yeah.
hyperparameters for the controller?
Yeah.
Oh, we would typically just set like kind of like a basic set that would work with like pretty much anything.
Yeah, in reality, we kind of run small experiments, right, and see the conversions and so on, and then see everything kind of working out. So we say, okay, let's run one.
I guess my question is, how do you control this over this long period of time that you're not diverging? You know.
You have to trust the IL. Yeah.
Did you have to iterate over this like after a long time? Maybe
I mean, actually, we found that the hyperparameters are fairly insensitive. Actually, so in almost every single AutoML paper that uses like the RNN controller, I think the same hyperparameters are almost used across all the papers. So it's fairly insensitive, I would say, to some of these things, as long as the reward is scaled accordingly for each of the different tasks.
Did we answer your question?
Yeah.
Okay. Yes.
I'm kind of curious. So, how well does like this like the neural network search architecture do versus like kind of the best in class possible? I guess that's hard to say for like some of these bigger search spaces. But do you guys ever try like maybe in a smaller search space, try to see like how well is its architecture versus like the best it could possibly do within that search space?
I see. How we gonna do that? Like.
Yeah, so the problem I think is like all the search spaces we've used have been really massive. So this hasn't been something we've really been able to test.
Yeah, you might want to use a microphone. Yeah. Can you turn on the microphone? Because I think there's some people online recording.
Oh, got it, okay.
Wait, well, can you ask did you say something else? Oh, okay.
But I think the real test is basically, can you design an architecture that solve let's say beat human design models on ImageNet, right? Maybe that's one way to think about it. So that's the next part of my talk. So we figure out that if you apply blindly the same principle to ImageNet right away, then it's too expensive. It would take months of effort, right? Because every single child model would take like a day to train or more, and then it's just too expensive. And then we turn to a new idea called transfer learning, right? So The idea is we went back and then we saw what Christian Zagady did. He tried to find like an inception cell, and then he would take that cell and he'll replicate it many times in the model. So we say, let's try to find that cell or like a composite layer, a kind of complicated layer. And then we can find it on a small data set, and then we transfer it over to ImageNet. So we actually set out to try it on, we try to find that layer on CFA10 and then try to transfer on ImageNet, and it kind of worked. So on CFA10, the architecture that we have was something like this. So we have some normal cell and reduction cell. So think about normal cell is like a traditional convolution layer, but it's just like a little bit complicated, and there's a lot of stuff inside it. And then reduction cell is like a pooling layer. It's reduced the resolution of the image. And then normal cell, reduction cell, normal cell. And then you replicate the normal cell many times, like the way that people replicate the convolutional layer many times. So this is the architecture that you have on CFA10. And then the controller will attempt to find the architecture of the normal cell and the architecture of the reduction cell. And on ImageNet, this is the architecture. We have a layer here called like a stem layer. People use it a lot in inception networks. So we say, okay, let's assume these two layers, and then the rest, we can just take these cells and put it there, and then this cell and put it there. Right? So this purely transfer learning, but transfer of the architecture, not just the weights. And these are the two cells that it found. It found a cell, the normal cell that looked like this. So first of all, it would take two layers before, and then perform a bunch of combination, like separable 3x3, and then identity, and then add them together. And then separable 5x5 and separable 3x3, add them together, and etc. So it creates the inception multiple branch architecture, and then concatenate at the end. And this is a reduction cell, right? And imagine you have to sit down and then design these cells. It's almost like almost impossible for me to actually come up with these cells. And it turns out that these cells work well on both CFA10 and transfer well to ImageNet. So let me go to the detail of what's going on behind the controller. So the controller first, it selects a hidden state. First of all, it makes two decisions. It's trying to select two hidden states here in a stack of hidden state that you had before. And then first it proposed like an operation that it can apply on one of the hidden state, and then another operation that applies to the hidden state, and then a method of combination. So going back. So to arrive at this node over here, first of all, it selects this hidden state, and then apply separable 3x3 on the first, and then, it selects this hidden state twice. And then it will say, apply separable 3x3, and then apply identity. And then the method of combination is add. So it selects it, and then the next step, it will select this one, and then select this one. And this hidden state is actually pushed back into the stack. So it could be reused to create another layer. So in that way, you can create a deeper architecture. But on the reduction cell, on the normal cell, somehow it doesn't like it. It just basically wants a lot of branching. Is it too complicated? Please ask questions. So the operation that it selects is either a identity or 3x3 average pooling, 5x5 max pooling, and etc. Right. So again, the controller will basically select one. So it select one hidden state, select another hidden state, and then it will basically apply one operation, apply other operation, and then combine. And initially on the input, we will have these two hidden states. And here's the performance on ImageNet. So on ImageNet, one standard way on ImageNet that people compare the models is compare the accuracy against the size of the model. Because there's something that people also see is that if you make the models bigger, you get better accuracy as well. So the fairest way to compare the models is to have this plot. So you have to see how many flops against the accuracy. And ideally, you want the accuracy to be at the top left of the figure. I think someone is pinging me, so I need to clear the chat. So ideally, you want your result to be on the top left corner of this figure, because that means you have less flops and more accuracy. Now, the black dots are human design models. And look in this figure, you might ask yourself what's going on with VGG, because it's actually quite inefficient. It's very famous, but it's very inefficient, and it's low accuracy. A lot of inception models belongs to like the frontier of human design models. So that's pretty good. The winning entry of last year ImageNet was SENet. This is another. This is one of the highest, but also most expensive models. And the red frontier is basically the network design by the controller. Actually, it designed on CFA10 and transfer to ImageNet, and got better frontier than human design models. Yes?
So is the reward function there accounting for the number of operations?
No. So if for some reasons it's actually learned to actually select better models and more efficient models. I think it might be the byproduct of like the asynchronicity of the training in the distributed setup. So the faster model train faster, and then send back the rewards faster to the controller, and the controller will sample those more often. So it's a byproduct of the asynchronicity of the training process. But it's kind of nice that like we actually shifted the frontier of the models up to the left. Now, turns out that like one model that looks very promising is this model right here. So it's actually as good as MobileNet models. So this MobileNet is very famous model. It's called MobileNet V1, I think. And the accuracy that we have is slightly better, like maybe 4 or 5% better. So when we take this model here, this red model, and then run it on the phone, it's actually slower than MobileNet. And this is because on the phone, it's different from GPUs, and the chip is kind of different. So it's actually it's better than in flop, and run faster on GPU. When you run it on the phone, it's actually slower. So we say, okay, now let's try to figure out that actually incorporating the mobile phone signals, right? The time signal. So we designed this framework where not only we get the accuracy reward, but every model we're gonna send to like a mobile phone farm. So we have a mobile phone farm of a few hundred phones. So every time we generate a model and train it, we send that model to the phone farm, and then get like a latency, and then we take accuracy and divide by latency and send the reward back. And then the controller will learn to adjust to find even better models. And better and faster model. So here's the result. I say, there's 2 plots, but maybe just focus on the left. It's better since it's on the left. So we designed a model called MNASnet. But before that, we want to take a look at the MobileNet v2. MobileNet v2 is currently, before this work, it's basically the best network that power on most of the phones that you use. That basically, you know, are behind Google Photos and so on. It's like one of the gold standard of the industry in mobile phone, neural net for mobile phones. And it's very hard to beat. We have a team of 10, 15 people working on this, designing this neural network. And when we started working with them, they said that it's very hard to beat this network because they spent, since they published their paper, they also spent a lot of time tuning it and trying to get better, and they couldn't get any improvement. And we got, I think we got maybe 2-3% improvement on the top one accuracy, which makes them very happy. And same if you, one thing that we also do is that try to change the depth multiplier. So take the network and then make it have more filters and so on. And it works everywhere, so that's good. Any question?
How you compare the two rewards? Is there any hyperparameters in there?
So I think the details in the paper. I think it's just basically taking accuracy and divide it by the latency. But then you have to have a little function to change the latency a little bit. You have some kind of cut off and so on. So it's not that complicated. It's basically essentially that accuracy divided by latency. So far, many people say, well, you have worked on a lot on ImageNet, so maybe you are already overfitting to ImageNet. Maybe some of the networks that you design overfitting on ImageNet. So what's the point? It turns out that because of our work, we also conducted a study of, say, how well, the real test. The reason why people do a lot of research on ImageNet is the hope that the networks will transfer to all the data sets. So we did a study where we took a bunch of data sets in computer vision with the VOC challenge, Oxford Stats, and so on, and we took a bunch of networks, so VGG, Inception, and so on, and then we measure the accuracy. We try to correlate the accuracy on ImageNet with accuracy on the data set of interest. So we have a bunch of data sets, flowers, and etc., and it turns out there's a correlation. So better networks on ImageNet do transfer to other data sets. So so that's good. We're not wasting our effort, I guess. That's the message. I think Barrett, you can the next part of the lecture. Barrett can tell you a little bit more about all the things as well. But if you have any question, please ask.
Okay, yeah, so for this next part of the talk, so previously we were talking a lot about kind of searching for finding the best architecture. But in this next part, we're going to kind of talk about the work that expands upon this and now starts to search for things that are non-architectures. So for example, searching for like a new optimizer, such as like momentum or SGD or atom, and also searching for new nonlinearity functions. So instead of using like a ReLU, we kind of search for new and novel things that can kind of help improve model performance. And like we were doing before, we use the same exact setup. So we still have this controller, and it will still propose some like sequence of integers like that we use to represent the architecture that then corresponds to some optimizer or nonlinearity based on how we kind of create this search space, which I'll go into. And then we sample like this optimizer or activation function. We'll try it on some architecture and look at how it does on some validation set for performance, and then based on this, we'll update the controller. So the idea is that over time, we'll be searching and finding better optimizers and nonlinearities, just like we were doing for the architectures. Yeah. So yeah, so like I was saying before here, the key idea with a lot of the architecture search stuff is that we can just represent each architecture as a string. And the idea is that we have this controller to generate the string, that we then take and then construct, and then we have some reward associated with this based on how well the architecture performs on some validation set. But we can apply this idea of having, of representing something as a string to these other ideas like the optimizer and nonlinearity too. So for example, for like the activation function, we can just represent it by some kind of like math equation. So for example, we could have like the sigmoid function where it's 1 over 1 plus e to the minus x. And we could represent it by a bunch of symbols by like having different numbers, different numerical symbols like divide and addition and exponentiation and various things like this. And so one work that we did was searching for new optimizers. So, you know, there's a lot of different optimizers used in deep learning like Atom, Momentum, SGD, like Adagrad, and various things like this. And so what we did was we parameterized a space of various different optimizers by having, so instead of, you know, predicting like a 3x3 convolution at this layer and a stride at this layer, now we just have the option to predict different operands, so whether we want to use the gradient, a moving average of the gradient squared, things like this, and then applying various operations to it like exponentiation minus multiplying two previous like operands together and various things like this. And so this approach, we use the same approach as we did for the architecture search things of where we'll sample an optimizer and we'll have some fixed architecture that's the same across all the different optimizers, and we'll train it on CFAR10 and see how well the generalization performance is. So here for finding the optimizers, we wanted to find optimizers that helped architectures generalize well. And then, so we again repeated this process, you know, like tens of thousands of times like we did for the architecture search. And here we can see the kind of top performing optimizers that we found. So at the top we see the performance of SGD, Momentum, Atom, and RMS prop. And then these next ones are kind of all of the like funky equations that are thing bound. And while some of them are actually pretty funky, some of them are actually really interpretable and doing really interesting things. So this is one of the ones that work the best. And so this is going to be the gradient times e to the sine of the gradient times the sine of the moving average of the gradient, okay? And what this is actually extremely interpretable and pretty cool. So what this is doing is that if the sine of the gradient matches the sine of the moving average of the gradient, so they're kind of both in the same direction, then multiply the learning rate by e. And then if they don't match, multiply by 1 over e. So it's like, you know, if they match, then we take a more like confidence step. If they don't, then we scale back. So yeah, so that's actually pretty cool that some of these things that we can discover are also pretty interpretable. Where with some of the architectures, they can look somewhat complicated, but here we can actually kind of get cool insights into really what's going on with this. Yeah?
Are you going to talk about how you generate the strings?
Of like the actual like exact search space? No, we didn't go into this, but it's actually very similar to how we have the cell of where we have this like bank of operands like the gradient, the moving average of the gradient, like the weight, various things like this. And then we have the option of like choosing two operands, applying a math function on the first one, applying a math function on the second one, and then applying some math function to combine them together. So I could take the gradient, I could take the moving average of the gradient, I could take the sine of both of them and then multiply them together. And that's, for example, how you would get the exponent of one of those.
So I guess your string is sort of like a stack-based language, like Forth or something, in how you're building programs from that string.
Yeah, we
Yeah,
kind of
that's
just
right.
iteratively. Yeah, exactly. That's exactly how
Yeah.
it's done.
So every iteration you fix your choice, or you can choose some. For example, in the 100 iteration you choose one type. In the other iterations you choose another type.
Oh, you mean so with training one model, do we switch like
Yeah.
part way through to change to a different optimizer?
Yeah.
No, with each of these we will like fix an architecture and we'll take one optimizer and train the model till convergence.
Do you think if you can stochastically, it can improve your performance?
Like to speed it up, you're saying? Like if we switched optimizers midway through training?
Yeah.
Well, then it's kind of hard to evaluate like the actual merit of each of the different optimizers. It can be a little bit harder to do that. Because like the convergence of these things changes depending on what epoch you're in. So it's kind of hard to evaluate like if you're using one optimizer, or like the first tenth of training on one optimizer for the last tenth of training, which one is really a better optimizer, if that makes sense. Okay. So then one of the other things we were really interested in searching for is nonlinearity functions. So in deep learning, especially in computer vision models, almost everyone uses the ReLU function, which is just, you know, like a 0 if it's less than 0, or like linear if it's greater than 0. And these are basically used everywhere, and I would say a lot of people don't really play around with changing it that much, especially in the computer vision space. And so with this project, one of the things we were interested in searching for is trying to find a better nonlinearity function for computer vision models. And so kind of like we were doing before, what we do is we would fix an architecture. I think we used like a ResNet model. But what we would do is we would kind of parameterize some space of activation functions with a very similar search space to the activation functions, actually, or with a similar search space to the optimizers, of where we'd have like a list of different operands, like the previous activation and various things like this, and then we would kind of combine them by applying math operations to them, like tanh, sigmoid, squaring, max, minning, and various things like this. And so when we ran the search and to kind of discover the best activation functions, the kind of the best thing we found was actually this function called, which we named swish, which is x times the sigmoid of x, which looks like this, actually. And if we can plot it right next to the ReLU function, which is the blue one. And so this is actually a pretty interesting function that our kind of search learned. So it actually looks very similar to the ReLU, but it has a few interesting components that people like never really experimented around with previously in activation. So here we can see that it has like this like negative dip right below the x-axis, and it also kind of has like a little more curvature on the right. And this is actually found to be very beneficial in vision models. And actually, when we applied this on like a bunch of different computer vision models, it was found to improve them in almost all the cases by pretty decent margins too, which is pretty exciting.
Yeah, two things that I want to mention. So first of all, during the search, ReLU was also found in the top 10. The swish actually came out on top. So it's actually, ReLU was quite well close to the optimal already, but this one works better. Actually, a lot of my friends in neuroscience actually told me there's some connection to the activation function that we found here to actually the activation function that they found in some of the neurons in the brain. But I don't know too much about it. But some, like Greg Corrado, my friend, he's actually very excited about it. The other thing is that actually it's basically right now it's quite adopted inside Google for many products that people use it in place of ReLU.
How was the computational efficiency this one compared to the ReLU?
Yeah, so it's slower, but you can actually quantize it. You can actually have like a discretized version of this, and it actually works almost as well.
And so one of the models that we tried this swish nonlinearity on is the like NASNet-A mobile model, which is at the time was like a state-of-the-art model. And so at the top we can see the top 1 and top 5 accuracy for ReLU. And yeah, of course, the higher the better. And so here we have like a baseline of like 4 of the other most popular computer vision nonlinearities. So like the ELU, the SELU, various things like this. And then below we actually have swish and one variant of where we have like a learned parameter associated with it. And we can actually see that we get some pretty big improvements. So even above the previous best across the other nonlinearity functions, it gets about like a 0.5% top 1 accuracy boost, which is actually a very big deal. Like if you look at some of the various inception models, like I think the difference between inception v3 and inception v4 is only about like 1.5% top 1 accuracy, which you can almost get from switching the ReLU, which you get from just switching from a ReLU to a swish beta for virtually like no extra cost, which is pretty cool. So here we can kind of take a look at like a very like basic view of a lot of deep learning and machine learning pipelines of where you have some data pre-processing, and you have some machine learning model, which is, was the focus of our previous AutoML stuff of where we would be searching for various components of the architecture and things like this. But one like extremely key component of kind of getting good performance across various tasks is actually the data preprocessing, and dealing with like things like noisy data, data augmentation, and various things like this to kind of expand the data set and make it more useful for these models. And one thing about the data preprocessing pipelines is that typically they were like hard-coded and manually tuned. And so one of the things we wanted to look at is like, can we also apply some of these techniques to the data preprocessing pipeline to see if we can kind of really improve the performance of some of these networks and data sets. Okay. And so the thing we were looking at is trying to apply these techniques to data augmentation, where essentially the goal is to just kind of expand and enlarge the data set. So like some very common operations you see used in data augmentation for vision is just applying like a horizontal flip, because typically whether the image is flipped or not, it's the same thing. So you just essentially can like double your data set size by just applying some simple transformations. And you can also do other things like rotating the image and zooming in on certain parts of the image, cropping the image, because it's all roughly still the same image, but it's still different enough that the model can still be learning different things from each of the different images. And so so here's the kind of picture of like a lot of the like AutoML-ish type work we were doing. And before we were doing the architecture, the optimization, and the nonlinearity. But again, now we can kind of expand this to even trying out for data augmentation. So now, instead of searching for the architecture or various other things, we would fix an architecture and optimizer and everything else on some data set, but then search for the augmentation like operations to be used. So whether to like apply horizontal flips on these images, whether to rotate the image, like, and various things like this. Okay. And okay, so we wanted to search for these augmentation policies. And so here we can see an example of like various different like augmentation operations and like the kind of associated strength of these operations, which we use in our augmentation policies. So to be able to search over augmentation policy, we need to kind of parameterize a space. And how we did this is the following. So we have a thing which we call an augmentation policy, which is just two operations applied sequentially. So here on the far left, we can see the original image. And then one over to the right, we can see that the two operations applied sequentially on this image are equalize and rotate. So equalize is slightly changing around the colors to normalize the like histogram of pixels. And then rotate is kind of rotating it to the right. And then next to it, we also have a probability associated with applying this operation for stochasticity. So here we see equalize 0.4, so that means on 40% of the images, we will apply this operation. And then, for rotate, we'll apply it on 80% of the images. And then to the right again, we also have some number between 1 and 10, which just simply specifies like the magnitude of how the operation should be applied. So it can be kind of thought of as the strength. So for example, with a rotate of 8, we might rotate it 80 degrees. With a rotate of 2, we might rotate it only 20 degrees, and things like this.
Yeah, and the transformation function came out of like image processing library. It's called PIL, the Python image processing library. Yeah.
Yeah, we just took all the operations. There's this PIL library, and I think there's like around 15 to 20 operations, and we just took all of them that were functions that allowed the input of an image and then outputted an image. We kind of just took like as many as we could to just allow this thing to search over. And so additionally, one thing we did was, so we have like 5 of these individual policies, and we combine it into one large policy for even more stochasticity. So what we'll do is, so when we get an image, we'll randomly select one of those 5 smaller policies to apply, and then apply that. So each image could have like one of those 5 policies applied to it.
Yeah. And the action that the controller take will be generate the function that it uses, and then the probability, the magnitude, and another function, the probability and the magnitude, and etc. So that would be the string that it needs to generate.
Yeah. So then we kind of ran this augmentation search on a bunch of different data sets, actually. So the first we ran it on was CFAR10. And the policies we found on CFAR10 we also used for CFAR100. And so here we can see the best published results prior to this, and then the best published results using our augmentation strategies. So if it was CFAR10 and CFAR100, these are actually like pretty significant improvements. So 2.1 to 1.5 is like a pretty massive jump in this, and it's actually still currently state of the art.
Yep.
And same with CFAR100. I think that, yeah, it's like a pretty huge improvement. And then same with SVHN, where we go to 1.3 to 1. And then on Stanford cars, we go from 5.9 to 5.2. And then on ImageNet with top 5, we go to 3.9 to 3.5. And so yeah, with almost all these data sets, we get like a decently large improvement with virtually no extra computational cost, which is very exciting. Yeah, because the training time doesn't really change, and at inference time, nothing changes. So with something seemingly as simple as just playing around with the augmentation with no added cost, we can get very large improvements. Yeah, so some of the current weaknesses of some of this AutoML work is that you still have to manually design the search space, which is actually a very time-consuming process. So for a lot of the different architecture search work and things like this, a big part of the success of it will come from actually designing a good set of operations to use that you can predict, such that the space isn't so huge that you can't find anything good in the 20 to 50,000 models you're gonna search for, but it's not too small that you don't really learn anything interesting. So it's kind of actually this black art to kind of design the search space. So instead of the black art of designing architectures, now it's switched to kind of figuring out how to best design the search spaces for these. And another problem is that the search methods are still really expensive. So for each data point for these methods, it's essentially taking a deep learning model and training it to completion on some data set, which is extremely expensive. And in some of these experiments, it takes a few weeks to complete, and using hundreds of GPUs, which is extremely expensive. And so there's a bunch of ongoing work actually of trying to make this much more efficient. And one of these methods that we were working on is called ENAS, where the key insight is that for when we're training when we're searching for a new architecture, we can reuse the weights of the previously searched for architectures to speed up the convergence. So before, with our architecture search method, we would sample an architecture, and it would just start with random weights, and we would train it to convergence. But now when we sample a new architecture, we can actually reuse some of the weight components of other architectures that had similar shapes that we could use.
So it's a weight inheritance. That's the idea.
Yeah. So then we don't have to train each model for as long, which can kind of drastically speed up the convergence. Okay. And so for the efficient neural architecture search method, the key insight is that we're going to look at the search space as just one large graph. And so, for example, if we're doing this for images, one could be the image, and then node 3 could be a 3x3 convolution, node 2 could be a 5x5 convolution, node 6 could be apply another kind of various operation like this. And then what we're going to do is we're just going to simply sample a path through this network, and then use those weights associated with that path. So each node in the network will have some weight associated with it, no matter what architecture path is chosen. So for example, every path that goes through 3 will be using the same set of weights. And so this can greatly speed up the convergence. So now when we sample a new architecture, we don't have to retrain the weights from scratch. And yeah, so one of the tasks we apply this on is image recognition. And so we tried this on CFAR10. And here we can see a huge speed up in convergence. So previously with NASNet A, we were using 450 GPUs for 3 to 4 days. And here with ENAS, we use 1 GPU for about half a day. And we can almost get the same performance, which is actually really impressive. So yeah, you get like an absolutely massive speed up by using the weight inheritance. So we can clearly see that this is definitely a good idea. Yeah, and another thing to note is that this was also done on the Penn tree bank experiments, and it works equally well, if not even better. Yeah.
So each time you actually sample a new architecture, you still train the weights. You just initialize them from the previous value for each edge.
Yes, that's right.
Yeah.
And do you train train that edge jointly across all architectures, or is it just basically repeatedly fine-tuned over and over again?
Repeatedly fine-tuned all over again. So like every iteration, you would sample an architecture, you train for a few iterations, you measure the accuracy, and then you send back to the controller, train the controller, and then sample another architecture, and all over again. So the weights will continue to improve over the time.
Yeah. So then here's the kind of more delicate question. If you then take that architecture and you retrain it from scratch,
yes,
do you get the same answer, or do you get a different answer?
So a lot of these experiments, we actually did exactly that. So we took the best architecture and then retrained from scratch. And we get better because during training, a lot of these things kind of influence each other. So it might stuck in a bad local optimum. So when we start from scratch, we get a little bit of improvement. But it's not like, I think it's not so much worse. For example, here we get 3.5, but if we train if we just reuse the best network, it might be like 4% or something like that.
So you share the weights in the architecture. The architecture is different how you share that weight.
Well, because we design a search space design a model that has everything in it.
Yeah, it's just one massive thing.
It's one massive model
that can
actually
contain everything it could possibly contain. Yeah.
So if you have a 1 GPU at home and you want to do an architecture search, that's one way to do it. So the person who did this, it was like a resident, and he on leave or at CMU, and he also had 1 GPU, so that he designed this method.
Yeah, it was done out of necessity, though.
Yeah.
Yeah, so then just to kind of conclude, like the summary of, do you want to say something?
Sure. Yeah, I think basically this is the takeaway picture, right? You do learn using machine learning to automate machine learning. So we have on the left you have a controller. Right, I've been talking a lot about reinforcement learning, but we also have play around with evolution, population-based kind of search method as well, and we also get equally good results, I would say. On the right, it's different components of the architectures or machine learning pipelines, you say, that you can optimize using this method. And the key observation is that a lot of these components, like architecture, optimization algorithm, nonlinearity, or optimization strategy, are like symbolic, right? So it's like a little program. So you can use your reinforcement learning to generate that program. And then you can score that program on the problem that you care about. And then that program you can actually send back to update the controller so that over time, with a lot of GPUs, you can actually find a good policy, like a good program. So yeah, that's the end of our lecture. I think if you want to know more about the literature around this, you can find in our paper, I think. Some references here for you to take a look, but we welcome questions.
Let's thank the speakers, and we'll
by the way, some of these ideas and algorithms here already deployed in Google Cloud AutoML So that if you have a model, I have a data set and you don't have a lot of knowledge about constructing models, some of the algorithms here can find the good models for you. Yes?
Is it more expensive to run AutoML or more expensive to hire software engineers?
Turns out we did the math and it's actually less expensive to run AutoML actually. So the experiments that we did for the CFA10 or ImageNet that get like 800 GPUs for 3 weeks or something, we did the math and it's not that expensive. It's like maybe tens of $1,000 or something like that, $10,000. I think I've heard that the New York Times said that like deep learning experts get paid millions. So the economics is about right. Any question? Yeah. Cool. Thank you so much.
Thank the speakers.
We're going to be here to answer more questions as well.
So as before, we're going to have the office hours, and the speakers will join us there. So if you guys want to discuss some more, please come to the office hours over in the usual place. And then once that's all done,
Thank you.
we'll release you guys.